Buongiorno a tutti, benvenuti. Per me è un onore essere qua adesso. Now I'll switch in English for the international audience, obviously. I'd like to start by thanking each one of you for being here. My name is Emilio Cozzi and I'm a journalist. My job is to write about space, but I don't write about space just because it's my job. I write about space because today, space represents our present and our future. And this is not rhetoric, it's a fact. Absolutely. It's not just our economy or our culture, it's our lives that today depend on space. And speaking of space and the safety of our lives, I think nothing like today's topic is relevant, because we will be speaking about design of spacesuits and extravehicular suits for microgravity, partial gravity, and Mars. I personally find these topics extremely interesting, and I'm looking forward for our guest speeches. But with no more delay, I would like to welcome Professor Francesco Cupertino, Dean of Politecnico. Francesco, the floor is yours.
Okay, good afternoon, everyone. Welcome here at Politecnico di Bari for this event. I join the welcome, the greetings to Daniel Olivas and to all the other guests, Roberto Vittori, and all the others. Roberto, I consider you as a member of the community of Politecnico di Bari, so you are not actually a guest here, but thank you for being here, for helping us organizing such events. I prepared just a few slides. I promise I will use them to go faster, not to take you too much time here for this part of my presentation. Of course, first of all, I would like to thank the Apulian Technological Aerospace District for being a partner of Politecnico di Bari in the organization of this event, and the Apulia region for the patronage, for supporting all our activities in this area. We are in the Apulia region. Apulia region is we have close to 4 million people living in the Apulia region, roughly the 8% of the Italian population. Of course, a region growing in economical sense is, if you consider the GDP product of Apulian region, we are the Italian region which had the largest growth after pandemic. So we are a region in which investments, most of all also in the aeronautic sector, are growing recently. This is a map of the main industrial players in the field of aerospace. And of course, we have Leonardo with Avioaero, that is a part of the G Aerospace group. And this gives any idea of the size of the aerospace sector in our region. And if on one side we have the companies, on the other side we have the universities and the research centers. We have 4 state universities and 1 private university in the Apulia region. And we have programs with most of them in the area of aerospace. We have courses with the University of Salento in Lecce, and we have also the PhD program in the aerospace engineering with the University of Bari. And then we had the chance of talking a little bit with Daniel Olivas before starting, and we mentioned about the infrastructure of Grottaglie, which was qualified in 2018 as the first spaceport in Italy, and is something that could host an infrastructure that could host a number of research activities also in the field we are talking today, because from Grottaglie we could start zero-G flights, for example, for experimentation, and we are also are studying the possibility of having a point of access to the space with horizontal takeoff and landing technologies, and that could another point of advantage of our region. Politecnico di Bari, I represent a relatively small technical university, but we are among the most important top 10 university in Italy regarding the number of engineers. We have almost 11,000 students and a number of degree and international agreement with other universities. Of course, we have started our teaching activities in the aerospace sector in the last 10 years, let's say, but we are pushing a lot in this area. We have both a Bachelor, Master of Science, and the PhD program, as I mentioned early. We are quite proud of being the Politecnico di Bari in this part of Italy. Also, the experience you will listen later about RIA Space. Somehow they started because, of course, they were good entrepreneur they had a vision, but they also had the possibility of talking and working with us in the development of what became the suite that is shown here this afternoon. That's the model that flied with Colonel Villadei almost 1 year ago. I recall that it was January 2024, the day of the flight. And then after that, we have a model of cooperation with private partners. We have 16 public-private laboratories that we host inside the Politecnico di Bari. Of course, the most important for numbers is the one with GE Aerospace that counts 100 people working, engineers from GE Aerospace working every day inside our laboratories, and we have a number of them. And then just going to the end of my contribution, I already mentioned the PhD and in aerospace science and engineering. I will jump to the last slide of my presentation. Sorry about that, but I didn't have the time to cut all the rest. Okay. Could you please just go to the last slide of the presentation? And I think that just the last one, if you go se andate direttamente all'ultima, mi mettete l'ultima, grazie. This is the structure of the PhD course, and also evidences which are the topics in which we can give a contribution. Of course, we have the aerospace engineering, the classic topics such as aerospace structure, fluid dynamics. We have a center specialized in computation for fluid dynamics. But we are also investing a lot in the aerospace systems and the application of information technologies and all the part related to the digital transformation applied to the aerospace sectors. And then all the part of the aerospace sciences. We have a joint department with the colleagues from physics department who are much more focused on such topics. I think that for sites, for geographical position, for the period that we are living, we can play a role. The future of aerospace will define the world in which we will live in next years. Of course, we have big players such as United States on one side and China on the other side. They will play the game. We have to decide in Europe whether we want to be the referees, that means that we will count zero in this game, or if we want to try to play together with them. I think that today we are trying to give a small contribution to the possibility for Italy, for the Apulia region, of being a player. We need to build up connection, to have agreements and the possibility of cooperation. We have to give value to the potential that we have in Italy. And of course, this will be just a small contribution, but a contribution in the positive direction. Thank you, and I hope you enjoy this afternoon with us. And just another word, if you need some, I'm very happy of the number of people that is exceeding our expectations. We have some more chairs and I will organize something that is compatible with the rest of in order to allow you also to have a seat this afternoon. Thank you again for your attention.
Thank you so much, Professor Cupertino, the Dean of Politecnico di Bari. Thank you so much also for hosting an event like this here. Thank you so much. Thank you so much. So, let us now get to the heart of today's proceedings. We will address the criticalities of extravehicular activities, and I would like to ask my question to today's first speaker. I know he will answer it. Why will extravehicular activities be an essential part of future advances in space exploration? Now, I shall leave the floor to Danny Olivas, US astronaut and AVA expert, president of Olivia and Associates, director of ICE Paso, sorry for my pronunciation, bad pronunciation maybe, and chief test astronaut and director of mission systems at Collins Aerospace. The floor is yours.
Thank you. Ciao. Everyone can hear me okay? So thank you for receiving this presentation in English because my Italian is terrible. So my name is Danny Olivas. I'm actually Mexican-American from the United States. I was born in the U.S., grew up there. So English is my native language, but I also speak Spanish because my relatives do come from Mexico. I've had the good fortune to work with some of your colleagues here in Italy, and I'll talk about that in a little bit. But you know, in the theme of what is happening in society today, we know that space is changing. Over the past several years, NASA has embarked on this program called Artemis, where we were going to be going to the moon and could very well still be going to the moon. But as happens here in Italy and every country, whenever there's a change in leadership, there can become a change in priorities. So NASA, just being part of the US government, is undergoing an evaluation right now internally to determine what the future of NASA is going to look like, at least for the current administration. Fortunately, the administration that has come to be was the one that initiated the Artemis program. So there's optimism that portions, if not all, of the Artemis lunar program will continue forward. And there's a possibility, though, that it could change because the NASA administrator will be changing. Previously, it was Bill Nelson, and now it looks like it's going to be Jared Isaacman. My role within the U.S. and within NASA is I served on the NASA Advisory Council. So we provided guidance to NASA. I still serve on the board right now. Provided guidance to NASA on the direction of the program, essentially as an independent reviewer of the space program. When I think about space, I think about my own personal journey. When I first decided I wanted to become an astronaut, I was really small. I was 7 years old. And at 7 years old, you don't know what it takes to become an astronaut. You just know that astronauts go into space. Now, at the time, I was in a program, or at the time that I was a child, we were going to the moon. We were part of the Apollo. I was part of I was a child of the Apollo era. So I first was introduced to space by people actually being on the moon. And it was then that I realized that was something that I really wanted to be part of, is part of the exploration of space. I used to, as a child, look through my telescope at night and see the stars and see the moon and just be fascinated by the fact that we were putting human beings there. Now, at 7 years old, you don't know what it takes to become an astronaut. You don't know what it takes to actually work in space. But what I did know as I grew up is that I had a proficiency in engineering, mechanical engineering specifically, and I found later that I also loved materials engineering. And it was that passion for engineering that led me to take what I could do very, very well. I went to school, got my degree in engineering, then decided to apply it into a field that I really cared about, and that was space. Now, I've been fortunate in that I've been able to become an astronaut. that itself took a long journey. My first application to become an astronaut went in 1988. And it wasn't until 1998, 10 years later, that I finally became an astronaut. And even after I became an astronaut, Roberto Vittori is actually a classmate of mine. We were in the class of 17. We both came in 1998. It took me 9 years after I became an NASA astronaut before I flew my first mission in space. Okay, so what does this have to do with the current administration and the current direction of NASA? First off is that we never really know what the future holds. It's constantly changing. And then the second piece is that it takes longer than we think it probably should. We live in a society today where we turn on our cell phones and we get an instant answer to any question that we might have. We can call, well, in the United States, you can call Amazon and get anything that you want immediately delivered to you. So we live in a society of instant gratification. The problem with space is that it takes a long time, and there's a reason why. Especially with regard to human spaceflight, is that safety is paramount. We've seen in our society when safety has lapsed in space and people have perished, that it could be the end of a program. So consequently, the requirements to actually build anything that is human rated takes a lot of effort. It takes a lot of testing, takes a lot of development, takes a lot of tries. And it happens a lot longer than you think it probably should. We know that when we have had issues in the past and we've had colleagues of ours, one of our colleagues, Roberto's and mine, Ilan Ramon, who was an Israeli astronaut, he was in our class, and he was one of the members of Space Shuttle Columbia that broke up over Texas on entry. When something like that happens, it's final. It's the end, not only the end of the life of the astronaut, but it also affects the lives that astronaut touched. And not only does it affect the lives that astronaut touched, like their spouses and their children and their family members, but also society in general. We think that space is a very safe environment now because we fly very often. We look at the success of SpaceX. You know, they've had very successful missions, haven't had any major problems on the human-rated vehicles. ISS, we put the International Space Station up in 1998, and we put people on it in the year 2000. And since then, we have had a continuous presence in low Earth orbit. We've sent people to the moon and brought them back, and haven't lost anyone along the way. But we also know that we've had in the US, Space Shuttle Challenger, Apollo 1, Space Shuttle Columbia. So the business that we're in is extremely, extremely risky. And as we sit here today and think about what the future of spaceflight holds for us, it doesn't really matter who is in charge, whether it's the US, whether it's China, whether it's NASA or ESA or Ozzy or whoever. Space is still space. It's an unforgiving environment. It's a destination that we as humans want to explore because we're curious by nature. But it's also a place that human beings were never meant to live. To live and work, we've had one home, and that's where we're all today, planet Earth. This is our only destination that humans have ever occupied and thrived in. Every other place that we've gone to, we have to work very, very hard to not die, whether it's the bottom of the ocean, even up at higher altitudes, like flying a plane. You know, you need the pressurized environment of the plane in order to stay alive at those altitudes. And then when you go into space, like low Earth orbit, you have no air, harsh radiation environment. tremendous thermal environment as well because of the radiation from the sun. Put it closer? Okay, I'm sorry. Thank you. And when we think about the other destinations, such as the moon and such as Mars, it's very similar. Now, we have been to the moon before, and I've heard this argument all the time. Why do we go back to the moon? We've already done that. Yes, but no. When we went there first, it was driven by political forces, and that was to the U.S. to beat the Russians to the moon. Once we did that, that objective was met, and there wasn't really thought behind, well, what do we do once we get there? This time, going to the moon has a different objective, which is one based in science, which is one based in resources, which is one based in sustainability. How can we keep human beings alive on the moon to conduct science? You know, what is there? Well, we've discovered since we flew the early Apollo missions, like when I was a child, is that there's water in the form of ice in the permanently shadowed regions in the South Pole. Now, the regions of the South Pole, we may say, well, it's still the moon, so we've already been there. We should just go. Take everything that we built before. Well, none of that will work in the South Pole. Even though the environment is the same, and you have the same lack of air, you have the same relative gravity, the permanently shadowed regions of the moon are extremely, extremely cold, minus 200 degrees Celsius. And they stay cold all the time. If we wanted to sustain a life there, we'd have to worry about things such as contamination. The dust on the moon has an electrostatic potential, which sticks to everything. It's a very sticky type of regolith, or dirt, that's on the moon. And it's very, very fine powder, because it hasn't eroded like it does here on Earth, because there's no weather systems on the moon. And those little fine particles get into textiles, like spacesuits, and start to abrade the textiles and degrade those textiles. They also find their way into joints, metal joints, that, you know, are used for articulation. Okay, so, well, why would we even send human beings to the moon? Well, no different than even today, why when we go camping or we go exploring, we as human beings want to know what's over the horizon. And we see that only by going and seeing ourselves. If we drove a car in the woods, you know, we wouldn't be content with staying in the car the entire time. We would want to get out, we would walk around, we would explore, because that gives us the ability to make decisions, to be able to see something and to turn it over and see what's there. You know, and if we were going to do something such as build a colony, you can't do it entirely with machines. You have to be able to put human beings as part of the construction crew. The International Space Station was conceived to be assembled in space, but even with all the technology that we have, we couldn't do it entirely just through robotic missions. We needed to involve human beings. Now, in the early days of human exploration in the Apollo era, you know, this was understood that we needed to put boots on the ground to be able to explore the environment of the moon. We built a spacesuit. And the spacesuit that was built back then was one that was based on the technology that was available at the time. It was heavy. It was very cumbersome. I tried to download some video to show you, and if you get online and you look up falling on the moon, you'll see the difficulties that the astronauts had, even just maneuvering around the moon. The environment of the moon, even though it has 1/6 of the Earth's gravity, because it has 1/6 of the Earth's gravity, the human being is designed and regulated to a 1G environment. And so when we're inside of a 1/6 gravity, we tend to operate as if our brain thinks it's in 1G. And so things such as center of gravity becomes very important. Astronauts were falling down on the moon because they weren't used to not having that gravity. Gravity actually helps keep us in place. So if you build up too much momentum on the moon and you don't have that gravity to hold you stable, you fall over. So there are environmental aspects of the moon which we know that we have to contend with because we've been there. And there's also aspects of the moon that we know that we're going to have to build up from our current knowledge, because we have some data available to us from the South Pole that tells us that this is a much more extreme environment. It's a lot colder, higher radiation levels. And remember, this is all about trying to keep the human being safe, especially if you're going to want to explore. And you want to leave the pressurized habitat. And when you go even further beyond that, Mars, you have a completely different environment. Here's one thing that everybody needs, all of us here today. We're all wearing clothes, that's good. We're all breathing air, which is nice. And the air that's circulating around us helps regulate our temperature. If we get too cold, we put on a jacket. If we get too hot, we take it off. So we do some self-regulating of our own environment. And even if we're doing nothing right now, as we breathe in, oxygen goes into our system, and we exhale carbon dioxide. But because the air that comes out of our mouth is warm and the air around us is cool, that hot air rises and it's replaced by cool, fresh air. If you get into a place like, say, low Earth orbit, where you don't have gravity acting on you in the same way, the buoyancy effect doesn't happen. As you breathe in and out, if you do nothing to move your exhaled air away from you, you just breathe in and out the same volume of air. And so circulation in low Earth orbit is important. But on the moon, you have 1/6 gravity, so you do get a little bit of a displacement that can help you. When you think about going to Mars, Mars is about 1/3 gravity, 0.38. It also has an atmosphere. So the life support system, which was designed and built for the moon, actually doesn't work on Mars. Because the Martian, just the little bit of a Martian environment that's there, that atmosphere, is enough to render the things that can operate in the vacuum of space now can't operate properly. So the entire life support system, whether it's how you keep your body cool, whether it's how you breathe, whether it's how you deal with CO2, these systems have to all be redesigned and reimagined. Now, I think we're living in a very exciting time right now, because there is a renewed interest in space. Whether you're talking about the US, whether you're talking about China, whether you're talking about NASA, whether you're talking about the Chinese Space Agency, or really any space agency that's out there, and even commercial enterprises, they're talking about space, about how to utilize space. Commercial space is a real thing now. We've seen that with Grotaille, Virgin Galactic signed an agreement with them. So human beings that are not astronauts, but actually private citizens, have the ability to have a taste of space, to get that experience. We've seen, for example, with the Axiom missions to the International Space Station, countries that never had a space program before are sending members, representatives from their country, to space via basically a private spacecraft. Blue Origin is building, not only do they have the ability to launch suborbital in a similar fashion to Virgin Galactic, but they're also building spacecraft that are destined to be part of the Artemis missions. There's outposts that are being designed and built and conceived to go around, just like we've been going around the Earth on ISS, to go around the moon. in a smaller space station referred to as Gateway. There are spacecrafts that go from Gateway onto the lunar surface, human landing system. Basically, it's a descent module that has to be able to descend to wherever it is the astronauts are going to be working and then leave from there. And all these systems have to be conceived and designed with one thing in mind, and that is keeping the human being safe first. Because if you can't keep the human being safe first, it doesn't matter what the mission objectives are. Now, there's lots of room in space for everybody. There's lots of opportunities for applying the skills and the capabilities to contribute to the space program. And as I have had the good fortune in working with Rhea over the past year and a half. So I was working for Collins Aerospace as a chief test astronaut for the new next generation spacesuit. Well, the company made a decision to not pursue that contract anymore, and so they basically dropped out. But during that time frame, I began having some discussions with Rhea. Now, why Rhea? Well, as it turns out, they built a suit that actually has biometric sensors in it and has electrostimulation sensors in there as well that are meant to try to counteract the effects of partial gravity. And it turns out if you build a spacesuit and if you have in your life support system mechanisms that are used to keep the human being alive in an idealized design system, you would want to be able to understand not only how do all those components work and how are they communicating with each other, just like any other computer system, like the computer system on your car. But now if you could integrate biometric sensors from the human being, you can now create a much more robust architecture of computer technology, potentially even integrate AI to be able to optimize the performance of the equipment by monitoring the way that the astronaut is actually working inside the spacesuit. And that was one of the reasons why we began talking to Flavio and Roberto and a lot of the people at Ria Space, because the idea was that, hey, can we take this kind of technology and integrate that technology into the next generation spacesuit? We have been to space before. We have done a lot of things. Every challenge has been unique and has been different, and it's taken longer than we expected it to take. But we know one thing for certain, that we as human beings look up at the stars at night. We'll never be satisfied with being able to just stay here and just assume that the universe around us exists and there's no need to explore it. We are curious beings. Not only do we want to look over the horizon and cross that horizon and find out about it, there are those of us that call ourselves engineers who are motivated by that. Because to me, engineering is about taking what you can imagine and turning it into reality by using the laws of physics and the physical world around us, the periodic table. Because that's universal. And as we create these creative solutions, we bring back technology to here on Earth. A spacesuit, you could say, well, a spacesuit only exists for space. A lunar suit only exists for the moon. A Martian suit only exists for Mars. But look at the very technologies that go into it. Those technologies can be used for everything from medicine. If I had a suit that had sensors in it that told me about the health of the person who's wearing it, that might be very applicable in a hospital environment. If I built a suit that was very robust and protected people in the harsh environment of space where there is no air, well, let me think about firefighters who can't breathe when they're fighting a fire. They can't breathe that hot air in, those noxious fumes. Even hazardous, material handling or the nuclear industry. These are all extreme environments where we as human beings work here on Earth. So these technologies that we're talking about developing for space don't just live in the vacuum of space. They have applicability here on Earth. And I also contend that as you think about where Italy is now and how it can play a role in the future, it's what technologies are currently built now for these kinds of environments here in Italy, and how can we extend those to space. Before space started, the companies that came to the table and helped build the space industry to what it was in the US never had space experience. They didn't start off as space companies. They started off as something else. And it's through that evolution of figuring out, well, how can I take this thing that I can do really well and extend it into a very, very hazardous environment, and what's required to do that. And those companies who met those challenges and who took on that initiative were the ones that became the space companies of today. Now, I believe personally that Italy is well positioned right now to be able to take the technologies that it currently has, take some startups and some innovative companies like Rea and some of the others that are here in the Puglia area, and extend those capabilities to a grander endeavor and contribution into space. I personally like spacesuits because human beings will always want to explore space, and they won't want to explore it from the confines of a pressurized compartment. They're going to want to get out. They're going to want to do it themselves, whether it's in low Earth orbit, whether it's on the moon, or whether it's on Mars. And I think it would be very exciting to see Italy be part of that next generation of space exploration. So thank you.
Thank you. Thank you so much. Daniel Ivas, I have a lot of questions, in particular about the debate between the moon and Mars, but so please stay with us because we will see you again today in the final panel discussion with all the other guests. Thank you so much. Thank you so much. So, in the next session, we will start to go into more detail talking about Martian exploration. We will do this with the company that designed the MC spacesuit, EMSI. Developed in collaboration with the Politecnico di Bari, the suit was used during the Axiom 3 mission, obviously, and it was awarded the Compasso d'Oro 2024 prize, maybe the more important design award in Italy, absolutely. So, now I'll leave the floor to Eleonora Zanus from Rea Space.
Thank you. Good afternoon, everyone. Thank you for being here. Thank you, Politecnico Bari, for having us today. So my name is Eleonora Zanus, and I'm here on behalf of my team, Rea Space. So as Daniel already covered most of my topics, I will try to go into more the details of what we are trying to do at Rea Space and what we envision for the future. So we are a very young startup, actually. We are just 3 years old. We were born here in Puglia, like 60 kilometers far from here, in the crop fields among olive trees, in a beautiful place. And we have a very specific target in mind. So we aim at designing and developing smart wearables and protective tools for astronauts, aka, spoiler alert, spacesuits. So most of the people know spacesuits for the bulky white miniaturized spacecraft that astronauts use to conduct extravehicular activities on the ISS or, for example, for Apollo mission on the lunar surface. But there is actually a wider characterization of spacesuits. And we started with a different product, which is the MC suit, to target a very specific yet very unknown problem that astronauts experience after human space flight. So basically almost all the astronauts experience physiological deconditioning when they are in space. So the biggest problem is actually when they come back to Earth, because they have to get used again to gravity. So, our bodies are in a constant and dynamic relationship with space, with gravity. So when you take off this from the equation, our body has to adapt again and again all over time. So when they come back to Earth, they have to go through months of rehabilitation to get back to use to gravitational load. So at first, they can't walk, or they have big problems to walk and to stand. And then you have to go through months of rehabilitation, as I said, hard training to try to recover. And most of the time, they even can't recover fully. So if they go through different missions through time, this is going to have long duration issues. So if we want to go to the moon, or even better, to Mars, we have to target the conditioning. Why that happens? So the skeletons goes through atrophy as they go muscles. We lose muscle strength, volume, and also the cardiovascular system, slowdowns, and all the fluids go up toward the head. This is going to create tons of problems. And astronauts today they have only one countermeasure that's actually working, which is training, training, and training. This is a lot of time. They train before flight, they train in flight, and they train after flight. But this is not just doable if we want to go to Mars, because they have to do that for 6 months, and then we are there, they have to get used to the different gravity that they don't know. So we came up with MC, which stands for Electrical Muscle Simulation. We developed it in partnership with the Politecnico of Bari and with the Department of Electronical Engineer. And basically, it is an intravehicular suit, so it's meant to be used internally in pressurized systems, so internal ISS or in spacecrafts, as a medical tool. So it comes with different sensors that basically monitor the body and the muscle activity, and they return an electrostimulation, an input that basically provides the gravitational load that's missing because there is no gravity. So what we are to try to do is to simulate and hack gravity, whereas gravity is not happening. So 1 year ago, we managed to fly with Axiom 3, and we started our first tests. We tested the suits and some of the subsystems. And this was a huge step forward for us, because actually gave us the ability to tackle the right targets and to decide and to focus on what we want to develop our know-how and how we want to step forwards. So the cool thing about this solution is it is driven by an AI algorithm. And this algorithm basically reads physiological data that are personalized. So my data are different from any other health here. And we return an output that is basically defined by the monitoring sensors. So it is fully personalized, and it's in constant development, meaning that we can use the same solution for microgravity, for lunar surface, or on the Martian surface, meaning that we can have one solution that works for all the gravities. So our idea was to develop MC also for the space travels to Mars, because once they get there, they have to adapt to 1/3 of the gravity. So if we manage to lower how muscle reacts to microgravity and to train them to a different gravity, which is the Martian one, for example, we can ensure a safer period when they're going to be on the Martian surface. But at some point, we were just discussing about his point, and we were like, okay, we get to Mars, we get them to be healthier than usual, but what's next? There is no spacesuit for them to conduct any extravehicular activity on the Martian surface. So we started thinking about a total brand new concept about extravehicular suit for the Martian environment, because no one has ever done that. And actually, there is a huge know-how that we can export to this new generation of spacesuit. So we started working on this new concept that was also presented in ESA 2 years ago, and won the space design competition. So from here, we started working on what we knew. So for example, in our case, our know-how is smart undergarment, and we started defining how we can transfer our knowledge to extravehicular activities. Why we need all this data? Well, we need astronauts to be safe, because extravehicular activities are one of the most dangerous activities that any human can perform, especially on an alien planet. So we defined some of the parameters that we want to target, from metabolic rate, heart rate, body temperature, of course, those are the basics. But we also go into more detail, defining how muscle behave, if they are overloaded with work, and so on. So we create a real-time monitoring that basically notify the astronauts while he's performing the activities. But once that you sensorized the human body, why not sensorizing the suit itself? Why not notify other crew members if any issues is happening? So I don't know if you're aware, but for example, years ago, Luca Parmitano, Italian astronaut, had a huge water leakage while performing an extravehicular activity, and he could not talk, he could not communicate to other crew members what was happening because there was water in his helmet. So for example, there is a huge opportunities here to sensorize the suit, to create a safer suit for them, but also safer extravehicular activities. So for example, one idea could be to create a real-time monitoring for the status of the suit, which is color-based, that basically notify the others about any kind of issues and failure of the subsystems. So at Space, we are very good at fabrics and smart wearables. So as I said, we are integrating different sensors to control human health and spacesuit health. But we are also working on how we can improve mobility of the spacesuits. Because, you know, extravehicular activity are extremely, create a lot of fatigue, physical fatigue, because you have to live within a pressurized microenvironment. So we are working on defining new standards for mobility using different materials that have never been used today to create a soft hybrid suit that is both flexible and rigid where you need to be. This we do with developing new materials or defining new fabrics that, for example, come from other commercial applications and have never been considered to be used in space, but actually they have high potentials. So, another field of research where we are focusing is integrating other type of tech. So what's cool is that in the last decades, basically technology has developed crazily, not just for AI, but sensors and application from other targets, other markets that have never been working with space, for example. So we don't need to develop everything by ourselves. We can look out at other market, other commercial applications, and define technologies that actually can be used and translated into spacesuits. Why so? Because for Mars, we need to define higher standards because they are going to have delayed in communication, so they won't be able to rely on mission control as they, for example, can do on the moon. So they need to be autonomous in everything they do. So we need to create spacesuits that not only can be defined as spacecraft, like miniaturized spacecraft, but also real assistant that can support them. So at the moment, we are working on different new subsystems. We're integrating new cooling system, which is one of the biggest problem of the current spacesuits because it's made with water, and water is a very important resources to save. Also, if you have a leakage, like for example, what happened to Luca Parmitano, this is going to be a huge problem to solve, especially if you are on the lunar or on the Martian surface. Coming back to the base, it's going to be more complicated, and you don't have much time. We are also integrating new technology in the helmet to improve communication, to mission control locally on Mars, but also to follow up with protocols, or, for example, emergency protocols, so that the astronauts can be guided by the suit itself and find the best way to get out of the emergency situation. Finally, of course, we are also working with technologies that have hit commercially all the market. For example, augmented reality so far is a well-tested technology. So why not implement all of this technology in what we need to achieve? As I said, there is a huge possibility to develop new technologies and come back them to the market on Earth. But we can also look at what exists already and translate them into the spacesuit of design. So this was it. Thank you very much for your attention.
Thank you, Professor Zanus. Thank you. I will see you again, the final roundtable, shortly. Thank you so much. Meanwhile, talking about new materials and talking about safety, the safety of our astronauts, good morning, in deep space could also be ensured by self-healing materials. But what are they exactly? And how can they revolutionize the design of spacesuits and EVA systems in supporting future missions to the Moon, Mars, and beyond? I would now like to call Antonio Mattia Grande from the Politecnico Milano.
So, thank you very much for the kind invitation. So, I am from another Politecnico, but doesn't matter. So, I will show you some research that I'm carrying out in my research group on new material for space application. In particular, today I will talk about self-healing material. I need to be honest. I didn't invent nothing. I just copied from nature. So self-healing material are around us. So if you check plants, if you check animals, or even our body, we are full of self-healing material. So these material are material that are able to repair itself after a damage. So we think our bones, our skin, or plants that are growing, then they can heal after a kind of damage that can create fracture inside the structure of the system. But how we can mimic what Mother Nature is doing in a synthetic material, so a material designed by humans. We have to just copy what we can find in nature. So we need a material that senses the damage. So when the damage occurs, we need that the material is aware that the damage is there. Then we need a trigger that actuates the delivering of the healing agent exactly in the region of the damage. And then we need to wait some times in order to have the complete repair or almost complete repair of the damage. If you check the biological system, this complete healing or almost complete healing can happen in years. So, for example, when you break your bones, one of your bones, it will take more than 1 year to recover completely, almost completely. This doesn't mean that you cannot use it in between. It can carry some loads, but do not have the same mechanical properties since the beginning, from the beginning. For a synthetic material, especially for a space application, we cannot wait 1 year to have a complete repair. So we need a quick reaction of our synthetic system and a quick repair in terms of seconds or minutes, depending on the kind of application. So this is the way to design new material with self-healing capability. When we have a self-healing material, if we are good enough to design a good self-healing material, we can have a switch in the design of engineering system. So until now, what the normally is doing is to check what is the best material for a certain application in order to meet the target in performance and reach the service lifetime that we need. If we have a perfect self-healing material, we can ask to the material to have a lower mechanical performance, but this material, thanks to the healing capability, will be able to increase the lifetime and recovery every time the same performance of the system. We are not still there, so perfect self-healing material are not there. Even in nature, it will be very difficult to have this kind of system. But we can have self-healing material that can show one healing event or two healing events eventually in the same location and still have an increment of service lifetime. So this is the target that we want and for our application. Of course, it will be very nice if we can design a perfect self-healing material. How is working self-healing? So we are copying by nature. The class of self-healing system from literature are divided in two. We have extrinsic self-healing system or intrinsic self-healing system. The former are characterized by some device or some feature that are directly implemented in the material. For example, we have a microcapsule-based system, so we insert inside the material microcapsule with a healing agent inside. So when a crack or when a damage appears in the material, the healing agent came out from the capsule and repaired the damage. This kind of approach came out from plants. So several plants have this system for healing different kind of damages. We have also another very famous self-healing system based on vascules, and this system came from our body. So we have blood that is flowing inside. When you have a scratch on your skin, you see the blood came out. I think that everyone experienced an event of this type. And then after a few days or few weeks, you have a complete recovery of the surface of your skin. Then we have another kind of class of self-healing material that is called intrinsic self-healing material. In this case, we do not add any device or feature inside the material, but we modify the chemical bonds inside the material to give the healing functionality. How we can do that? By adding different kind of bonds that are reversible, that can open and close depending on the environment, for example. Also this one, I should admit, came from nature. So these kind of bonds are, for example, hydrogen bonds, are physical bonds that are reversible, and we can find in our DNA, for example. We have covalent reversible bonds that are the disulfide bonds, sulfur-sulfur bonds. In this case, these kind of bonds are bonds that we can find in our hairs, for example. So still biomimicry copying by nature. For the nature of this kind of bonds, the intrinsic self-healing system are usually applied to polymeric material and composite, while extrinsic are applied to different class of materials, so composite, polymer, but also concrete, metals. So there are different examples of extrinsic self-healing system already also on the market, applied with all class of material. Let's move to spacesuit. So why self-healing material can be useful for spacesuit, especially for extravehicular activity. So spacesuit can have different kind of damage, from abrasion with regolith, for example, with the puncturing, with different tools. We have fatigue, so the bending of several times of flexible part of the spacesuit can create damage, especially for very long mission. And this can also be a risk for the astronaut, especially perforation. So this is an example of a damage of spacesuit during an extravehicular activity. The idea that we have in mind is to create a material that will be able to heal this kind of damage. For example, perforation that are the more risky for extravehicular activity. How we can do that? There are different strategies. We try few ones, and then at the end we select the one that we think is the best. So let's make some example of strategies to give synthetic functionality to a spacesuit. So spacesuit is a multi-layer system. We have different layers of material with different functionality. We have the external part, the bladder, that is the internal part. Each of the layers have a single functionality. The idea to give self-healing functionality is to add one layer with a healing capability. The layer can be different, and have different capability of heal depending on the interaction with the external system. For example, we can use an extrinsic approach with microcapsule. So when we perforate the spacesuit, when there is a damage in the spacesuit, we break also microcapsule that are filled with a liquid that can react with external environment. For example, radiation, UV. We tried this system and we found some drawbacks because have a liquid inside a spacesuit can be risky. So we can have evaporation, we can add leakages, so it's not the best option in my opinion. The same for chemical reaction. In this case, we still put liquid inside. When we have a damage on the spacesuit, two liquids came out and react each other in order to seal the damage, eventually seal the damage. Also in this case, we have the same problem of the microcapsule. Liquid inside a spacesuit can be a risk for a final application. Then we have other two mechanisms. So it's called mechanical coverage. So we put a pre-strained layer of elastic material or elastomeric material inside the spacesuit. When we create the damage, this foaming material is flowing in the internal part, sealing the damage. Can be a good option for instantaneous healing, but not probably for a long period healing. The other option, the one that we choose for our research, is linked with the flowing material. So it's a viscoelastic material that is able to flow in the region of the damage and sealing the damage by exchanging of dynamic bonds exactly in the region of the damage. So in this case, we have the trigger, that is the puncturing of the spacesuit. We have the moving of material in the region of the damage, and we have the time of healing that is dependent on the reaction kinetics of the dynamics bonds inside the material. So we are mimic the synthetic route that I showed in the previous slide. To do that, we need a testing protocol. We start with material processing. We choose material processing, polymeric material with processing that we can do in our labs, so nothing complicated. We select a protocol for self-healing assessment. In this case, was a cylinder with inside our self-healing material, a pressurized cylinder with self-healing material. And then the last part is the response to space environment. So this material need to be space-proof, so space-grade material. Let's start with the selection of the material and the design of the material. We use, for example, one material, an elastomeric material based on epoxy. That is the material already used in space application. It's one class of material that is called the supramolecular polymer, thanks to the reversible physical bond that are inside the material, H bonds. The other material is a polyurethane material with inside both physical bonds, H bond, and the sulfide bond that are the covalent bond that are able to reconnect after damage. For both cases, we are playing with the amount of reversible bond inside the material to tune the viscoelastic response and the healing response, so the kinetic of closing the damage and sealing effectively the damage. We work coupling this material with other layers, in particular fabric layer and other elastomeric layer, in order to mimic the stacking sequence of the spacesuit. And also, I will come in the last slide, we are working with nanocomposites, adding nanofillers inside this self-healing matrix in order to give new functionality, other functionality to the self-healing system, in particular for conductivity, electrical conductivity. So starting with this material, we design our testing protocol, a pressure vessel filled with gas, can be air, can be argon, nitrogen, depending on the application that we want. We have one side of this pressure valve sealed with the specimen that we prepared, and then with a standard tensile machine, we puncture our material following the flow, the time that the system take to close and seal the damage. The system is able to record the flow rate, so how much gas we lose during the damage event and the healing event, the peak flow rate during the damage, and then the minimum flow rate that for us is the indication that our system is working. So to have a complete healing, we need that the minimum flow rate is going to 0. So other parameters that we take is as a benchmark to evaluate the healing performance are the time that is passing from the peak flow rate to the minimum flow rate. So a quick system heal in few seconds, a medium system heal in a few minutes. So depending on the chemistry that we are using to design our material. Some example, so with one of the material that we used, already directly with the multi-layer system. You saw here the different performance of a stacking sequencing, coupling the self-healing polymer with the aramide fabric. You see that we make several repetitions, but in this case, we have sometimes a good healing response, so sealing of the damage after puncture. In other case, the system is not going to 0, so it's not able to completely seal the damage. The answer is why? Because some fibers are going inside the hole. So the coupling with self-healing system directly with the fabric is not a good option. For that, we move to another stacking sequence, coupling the self-healing system, the self-healing polymer, with another elastomer. In this case, was a silicone elastomer already used for some application in space. And this gives us a good self-healing response. Was very quick and also with a minimum flow rate respect to the other case. Why? Because the elastomeric material is helping the closing, the sealing of the damage. In this case, we have a contact with the aramide fabric. Fabric do not help the closing of the holes, while an elastomeric system, so an elastic material, is helping the sealing. This is because the self-healing material is a viscoelastic system. It takes some time to flow and seal the damage. Coupling that with a more elastic material is reflected by a faster healing response of the multi-layer system. Another example for the other material, so here we pass with the polyurethane system. In this case, we have similar good response of our material, but with a lower thickness. It means that we can reduce the amount of self-healing material that we put in our spacesuit. We did the same as the previous case, coupling with aramide fabric, or coupling with a silicone elastomer, and also in this case obtaining good data. So low peak rate and a quick response of our self-healing system. So it's going to 0 and then a complete seal of the damage after puncturing with a needle of a diameter ranging from 2 millimeters up to 5 millimeters. So a very big puncturing inside our system. Checking the result with all the families or all the different architecture of material that we used, we found one of the best options that give us the minimum flow rate, the minimum time after the damage event and the complete healing. And this was the system that we select to study more in deeper for space application. What we do next with this material, we perform testing for space application. In particular, outgassing test. So all the material that are going to space need to be certified or qualified by a space agency. In this case, we went to ESA to test the outgassing performance of our self-healing material. Luckily, one of the material have already the performance in line with the space requirement of the European Space Agency. Next test that we did is a radiation test. So we evaluate the performance, the self-healing performance of our material after gamma radiation exposure. And we check that there is a minimum effect on the radiation. Of course, there is a change in a chemical architecture in the material after exposure to radiation, but still the material is maintaining good healing performance after exposure to this kind of radiation. What next? The next step is adding nanofillers. In this case, we choose carbon nanotube to give new functionality to our healing system. The first thing is to check if our material with fillers inside is able to heal, and this was the case. So adding 1% of nanotubes, multi-walled carbon nanotubes, do not affect the healing response of the system, but give us the possibility to increase of 2 orders of magnitude the electrical conductivity of the material. Why we are doing that? Because we want to apply this material also for electronics. So in order to have a multifunctional material, a totally multifunctional system inside a spacesuit, and reduce the weight of the spacesuit, we cannot only add a self-healing layer for self-healing. We add also electronics. We want to add also electronics inside the self-healing layer in order to monitor the activity of astronaut, like was presented in the previous presentation. It's a project that is running. I hope to give you new data or new information of next time. So to conclude, we found a promising class of self-healing material, self-healing polymer for space application. With already good mechanical properties and space-related properties for application in spacesuit. There are still some drawbacks. We just tested few environmental aspects of space, so radiation, outgassing, but it's important to test also the synergistic effect of different space threats. So we have also thermal oscillation, we have different kinds of radiation, UV, we have atomic oxygen, depending on the application that we want. But we are in the good track to make our test. With that, I would like to thank my university that gave me the possibility to be here, the founding agency, so European Space Agency and the Italian Space Agency that found a project on this research, and also the Italian government that recently found a new project on self-healing material for space application.
Thank you.
And also thank you for
Thank you, Professor Grande. We will also meet you in the final round table, so take a seat, but stay with us. Thank you so much. Thank you so much. More and more people are talking about space and blue, about the clear relationship between marine and space explorations. Oceaneering International, founded in 1964 in Houston, Texas, is a global leader in advanced engineering solutions and robotic technologies. Initially, it was specialized in the offshore energy sector, particularly in deep water application, whereas today it works in the sector of defense, aerospace and entertainment. So, I will leave the floor to the ex-EVA integration project lead and human systems business development lead at Oceaneering Space Systems, Ms. Adele Luta. For the next 15 minutes, the floor is yours.
Differently, I'm going to take a poll, so if you'll participate. Put your hand up, and you can put it up more than once if you cross-train. So where are my engineers in the room? Who are my engineers? All right? Yeah, Danny. All right, and then where are my medical people? So doctors, nurses, or biomedical engineering, any medical? Okay. How about any scientists or mathematicians? Okay. And programmers? Any programmers? Okay, in the back, like it. And then how about other? You know, all those English people and I don't know, you know, political majors. Anybody else? Anybody dare? Journalists, maybe? Oh, there we go. Okay. The reason I mention that is because I think that there's a perception you have to be an aerospace engineer to work on these projects, and the spacesuit could be more not that case. You really need, our teams are multidisciplinary. We're pulling almost every meeting from multiple different areas, and that's because the spacesuit is so complicated. So, you know, a spacesuit in itself, which I love spacesuits, is a vehicle that has to do for a short period of time everything we ask of a full space vehicle. But, bonus, we have to move in it, and it can't damage our bodies too badly. A few bumps and bruises is okay. But also, we have to be able to get it through the vehicle. So it has to be small enough, and I'm going to show you a video to kind of emphasize that point, that it has to be a vehicle within a vehicle. So we have to be able to get out and in of whatever vehicle is housing us for that longer term. So it has to do a lot of things. We're asking a lot of things of a space vehicle, aside from, hey, just keep us alive. So it really is amazing. I think it's one of the more challenging vehicles to work on if you're thinking about going in this field, regardless of your background. Take a look at spacesuits. It's very cool. Okay, so, yep, if you want to put the website up. Okay, so as I said, I work for Oceaneering Space Systems, and one of the things that we like about individuals that work at our company is not just their background, but what they also do. So how many of you in the room are scuba divers or have ever scuba dove? All right. How about hikers? Anybody's gone up to high altitudes, thin air? Okay. How about just regular backpackers? How many of you have carried a pack on your back that's pretty serious? Okay, what was the heaviest pack that you carried?
Maybe 5 kilos.
Okay. How about, wait, who else? You raised your hand? No. All right. So, you know, if you're going long distances, sometimes those packs can get pretty heavy. And those are all good experiences which allow you to start to understand potentially what it's going to be like in a spacesuit. So at Oceaneering, we actually work in both environments. We work under the water and we work in space, and we have offshoots as well. Some of these vehicles here are used in entertainment. This is one of our ROVs that we use to support oil and gas in monitoring to keep those pipelines with minimal exposure to the environment. If you can scan down. And we are an international company, so go ahead, keep going. A little bit, if you want to keep going. Yep. So we're based in 24 countries, so even though our headquarters are in Houston, Texas, we are all over the world, and we really, our kind of tagline is solve the unsolvable. So a lot of the people I work with, we really get excited when someone says, this has never been done before, or we can't figure out how to make this work, can you come help us? And we are right there, we're right there to work with you. Can you keep going down? All right. So, like I said, under the ocean and space are the two big areas. So I joke that if it's trying to kill you, that's where I want to be working, because that's exciting. Keep going. All right, and safety and integrity, honesty is really, really important in our company. So if you are thinking about getting out, we always have our career page. Again, we can take you to all different places in the world, and we're always looking for people that are really willing to take on that challenge. That being said, I want to spend a few minutes, and I know I have only 15, focusing on a video of a test that we did recently, and this is, you can Google this is open domain, of some of the new testing that Danny mentioned. So Collins, Oceaneering, and ILC Dover was working on a suit together, and one of our testing objectives is we had to fit through the airlock to get out into space, so that vehicle within a vehicle that I mentioned. And we decided to do that test on a zero-G flight, which meant we had double the team members, because at any point we had to be ready for half of the people to get sick. And we hoped not more than half would get sick because we had to complete the test. So can you go to the video? What I'm going to do is I'm going to let you watch the video first. It's a short video. And then we're going to watch it maybe about 2 to 3 more times. And I want you to focus on different things that I'm going to point out to you, because there's a lot going on in this video. All right. All right. So this is a spacesuit, and they're working to get out of this hatch, which would be going out to the vacuum of space. And you'll see that we were successful in getting it out. All right. So we're going to pause there and go ahead and start the video again. So the next time you watch it, the thing I want you to focus on is this guy right here. And you're going to see when we go to a microgravity environment, you're going to see him pop up, and he's holding on with his hand right here. So it was only a few seconds before we had to get up, and then now everybody's going to come right back down. And our goal was to get that suit outside as quickly as possible. He's pulling the umbilical here, which is providing that pressure. So you'll see everybody come all the way back down, and we had to get the suit down. So we're talking about a matter of, we had parabolas that were 12 to 18 seconds. I mean, they were pretty short that we had to do each test objective. Let's watch it one more time. The other thing is we had to control and help the suit get up. So this is me right here. In order for me to help lift the suit, and you'll see me remove my hands to show we're not pushing the suit, I had to lock my legs under the airlock mock-up. So at the end of the day, I had big bruises on the tops and bottom of my legs because that was the only thing I could get to shove myself in to then move the actual suit and then let go of it. So it's a cool video because there's just so much going on. But it shows you that we really have to try to look at these other environments in order to get these objectives done. Because at the end of the day, space is a unique environment that the only way we get to that mature TRL level, for sure, is when we go to space. So we have to use under the water, we have to use zero-G flights, we have to use 1G environments with weight relief systems to try to get all of this testing done. So it was an exciting test to be part of. It's some of the stuff you get to do if you work on spacesuits. And it was just, yeah, it was a good day, a good 2 days that we did. So, all right.
Thank you so much. Claudia Luzza, please to join our roundtable later. And now it's time for the second session of the day. Access to funding is a key factor for startups operating in the space technology sector, as it enables them to develop cutting-edge solutions and compete on a global scale. So now I will leave the floor to the Program Manager, International Business Promotion and Inward Investment of Puglia Sviluppo, Teresa Malloy.
Thank you so much, and it's a great pleasure to be here, and thank you for having me. Even though I'm not an engineer, I was glad to find out there are a few more non-engineers in the room, because I deal with something that everyone likes to talk about, but I think companies working in space need a lot of, and that's money. I work for Puglia Sviluppo. We are a regional government agency. We're the public finance company, and we basically manage all funding initiatives for companies investing in innovation. Obviously, there's no progress without innovation, and innovating in the aerospace sector, whether you're a startup, whether you're a medium-sized company, or whether you're a multinational, requires a lot of capital, because it's a very capital intensive business. And we don't have huge amount of funds, but the money that we do have, we try to channel them into worthwhile startups and successful business initiatives in various business sectors, but we are currently focusing a lot more on high-tech and innovative business sectors. This is just a little bit of information on what public funding can actually do. Here I'm talking very quickly about what happened with our previous funding programs, where the funding dried up, although it says 2014, 2020. Basically, just last year we finished handing out the money that was available. And over that period, we helped over 960 business projects get off the ground, projects worth over 8.4 billion euros, and the regional government put up 3.5 billion euros for those initiatives. Obviously not all in the aerospace sector, but a good number were. And what can you see happening here with the small graphic that I put on here? You can see how much the GDP in the various regions of Italy grew between 2019 and 2023. That's in the period of the pandemic, or right after the pandemic. And what we see here is that Puglia is the region that grew the most. Our economy grew the most. And we like to think, it maybe not be true, that that's because a lot of our companies invested in innovation. Almost 1 in 2 companies in the region invested in innovation in 2020. And that obviously put them on a much better footing to be competitive, to be out there with new products, with new ideas, with new business solutions, and get through the pandemic and get back onto the international market. And another thing that the regional government invested in during that period was also making sure that the companies in the region have access to the internet, and we were the first region in Italy to overcome the so-called digital divide. I presume that a lot of you know that Italy, or Puglia, is considered one of the regions which is a late developer within the European community. But as I said, we were the first one in the whole of Italy to overcome the digital divide. And that, again, is because of regional government investments in that area. This sort of translates for us into the region becoming more and more attractive for startups, and I'm talking about high-tech startups and innovative small, medium-sized enterprises. At the moment, we have over 700 operating in the region, and that's quite a big number for us because Puglia is a small region. There's less than 4 million inhabitants in the region. Although we do have over 300,000, 320,000 companies operating in the region. And that's because there's now a lot of attention to getting startups off the ground. And there are 3 certified startup incubators in the region. And we were very excited that last year the Extra-Vehicular set up a startup incubator here in Puglia, in Brindisi. And I believe that you'll be going there tomorrow. To see what they're doing and how they're helping startups in the space sector get off the ground, providing funding, but also all sorts of assistance. Why are startups coming to Puglia? It's not just for the money, because we can't really give that much, but I'll talk about that later, although it's quite a good way to start up. It's because there already is a very important, what we call the ecosystem for innovation. There's over 450 public-private entities operating in innovation, helping out startups, helping out companies, helping out even multinationals carry out research and state-of-the-art research. There's 25 National Research Council institutes with their labs here in the region. There are 6 technological clusters. One of them has been mentioned before by the Chancellor. It's the aerospace cluster, which is a non-profit consortium, again based in Brindisi. They're the ones that manage the Extra-Vehicular. We have ENEA. We also have 5 European digital innovation hubs. Obviously, none of this would be possible without the universities, the university system. There's 5 of them in the region, and they not only help a lot of companies carry out their research, just as they've been doing with REA, but also with many more. In fact, the Chancellor also mentioned the research centre, the joint research centre with GE Avio, which is a multinational aerospace company. But also, thanks to the universities, we have an important talent pool, which again is another reason why more and more companies are looking at our region and thinking about coming here, because they know that they can find qualified graduates who can help them get their business plans off the ground. Before I talk briefly about the incentives and the help that we can give to startups in the space sector, I wanted to mention a little bit about the aerospace industry within the region. Again, this is because when we meet with potential investors, they usually don't think that they're going to find high-tech or aerospace companies in Puglia, and we do like to prove them wrong. The aerospace industry in Puglia has been going since the 1930s. It's not something that just happened a couple of years ago. a lot of companies chose to move to Puglia or to set up business units in the region. Again, as I said, not just because there was public funding available, but because of everything else that happens within this region as far as what the university can do to help them do their research. And again, the new ideas, the new startups that are coming into the market. We have big companies such as GE Avio that I mentioned before. They've been working on this catalyst motor, this engine for the Eurodrone, and it has been funded, this project was funded again by the regional government through our incentives. So there's a lot going on. We have over 450 SMEs and startups working within the aerospace and 50 large specialized aerospace companies. So it's a very dynamic business sector in the region, and we do a lot to try and promote that and get more businesses to come to Puglia and look at what we're doing in this sector. How? Well, as I mentioned, the regional government has set up a whole raft of business incentive schemes. During the last funding period, we have over 12. At the moment, we are now working with the new European funds for the period 21-27. At the moment, we have 7 funding programs available for companies, be it startups, SMEs, or the multinationals. And most of these funding initiatives provide both financial aid, that means it's cash, it's non-repayable incentives that we hand out to companies that have obviously interesting business plans, and also repayable loans. So this allows companies to be able to get access to quite a large sum to help them get their projects off the ground. What do these incentives cover? Obviously, they don't cover 100% of the costs for companies, but they do put out a substantial amount or percentage of the costs for research and development, plant investments, staff training, environmental protection measures, innovation and business process re-engineering, as well as business consultancy and international business promotion initiatives. I'm not going to talk about every incentive scheme that the regional government has on offer, but just I wanted to focus quite quickly on 2, which I think may be of interest for who's here today, who's taking part in this meeting. One is called Technonidi. It's a scheme that was devised specifically for technological startups. Rea Space is a beneficiary of Technonidi, as are many other startups in the space sector or aerospace sector, some of whom are now multinationals themselves with companies, especially in America, working with NASA. But Technonidi was set up in 2017, and over the past few years, from when it was set up until last year, when the first call closed down, we had 412 applications. So I mentioned before we have over 700 startups in Puglia now. We didn't have 700 startups in 2017. We had a lot less. But looking at how these startups have grown, the number has grown in Puglia, we're quite confident in saying that at least 1 in 2 of the startups has benefited from the Technonidi scheme. What does Technonidi make available to companies for startups? It makes available up to 280,000 euros in funding. 100,000 is for investments in tangible assets and intangible assets. That means if you have to buy a software license, or if you have to buy someone else's research, or that's intangible. Tangible, obviously, if you hire an office, if you buy some computers, you buy some machinery. And we can cover up to 80% of those costs, giving companies 100,000 as a grant payment, so that's non-repayable, and 100,000 as a repayable loan, basically with 0 interest. Also, we can give up to 80%, up to 80,000 euros for operational costs, which very few funding initiatives for startups do, because obviously operational costs, it's something that nothing remains at the end of the day. It's something that can't be resold or recuperated. But it's very important for startups to be able to pay their staff's wages and to be able to cover their operational costs. So the government has made available 80,000 euros for that. All of these, let's say these funding levels are available to, as I said, startups who can't have been operating for over 5 years, and to have interesting projects in innovative sectors, which are linked to the so-called regional smart specialization strategy in areas such as sustainable manufacturing, which obviously includes aerospace right across the board, from new materials, automation, robotics, technologies for propulsion, and so on. So we try to put everything in there linked to aerospace and what's happening in aerospace in Puglia at the moment, as well as human and environmental health, digital, creative and inclusive communities. Since we opened the new call in November in 2023, we've already had 117 applications for projects worth almost 29 million euros. So we're quite confident that the Techno-Needy scheme is working. However, we did think about what we could do to help companies, especially startups, after they've already had maybe some funding from Techno-Needy or other funding from small startup programs. How do they begin to ramp up their activities? As I mentioned before, and it's also come out from the other speakers, this is a very capital-intensive industry, especially space. You need to invest a lot before you start seeing returns. So it takes a long time to actually get a final product out there onto the market that you can actually start selling and start generating revenue from. And very few companies can do that on their own. So public funding is very important. And that's why we thought about creating our own equity fund. So a fund that will give companies the possibility of looking at more medium to long-term plans and begin to take their research forward and move towards, as I said, getting that product and getting it onto the market. So we created the Equity Puglia Fund with an initial endowment of 60 million euros. How does it work? Obviously, we are not a private funding company. We don't manage assets. We manage public funds. So we decided that we would, in a certain sense, go into business with who does that for a living. And so we decided to put out a call, a public notice, for asset management companies to come forward and to put their resources into the equity fund, and their resources will be matched by the regional government's resources. So what happened? We put out the call in 2023, and we so far have 4 asset management companies. Each one has committed 10 million euros to the equity fund for a total, therefore, of 40 million euros. And Puglia Sviluppo has committed the other 40 million euros. So that means there are now 80 million euros available to companies, startups, or small, medium-sized, innovative enterprises who are looking for equity funding. That means someone comes into your company, puts money into it. Obviously, they want it back, but not next week and not next year, in the medium to long term, as I said. And that depends on the financing arrangement that the asset management company. So these are the 4 asset management companies that the region has selected or that Puglia Sviluppo has selected, and we already have financing agreements with them. 3 of them are based in Milan because that's the financial capital of Italy. Some of them have already funded startups from our region, not with the Equity Puglia Fund, but with their own private funding. And we have one also in Naples, so that's pretty nearby. What do these companies do for us? They look for the projects and the companies to invest in. They then manage the principal fund, which is their money, and they manage the co-investment fund, which is the money that Puglia Sviluppo has put forward. And then they carry out the investment, as I said, in the target companies, setting up the financial agreement with them. Who is a target company for the fund and for these asset management companies? As I said, startups, okay. They can't be already listed on the stock exchange, so they must be unlisted companies, which means obviously they haven't already had access to private funding. They must be based in Puglia. They must have a medium long-term to long-term business plan for developing new products or services and getting them out there onto the market. Again, in the same business sectors that we saw before for Tecnonide. So that does cover everything in space and aerospace. The type of equity investments that the AMCs make, obviously, are the typical ones, either directly in equity, so that's giving the company risk capital, or they can buy up existing shares if there are, and then resell them, obviously, to the company at a later date. How much is available? Maximum 5 million euros from the co-investment, that's the public funding, that has to be matched by the private funding. So that means that one single company can receive up to 10 million euros in funding, in equity funding for their initiative if it's suitable. And the investments must be completed by 2029 at the moment. Then we'll see how that pans out. Because if you noticed, I did say that we had 60 million euros available. So that means we still have space for 2 more AMCs that we will probably actively look for throughout this year with another public notice. And that would make yet another 20 million euros available for the companies. So these are the main initiatives that I wanted to talk to you about, but obviously we do have many other funding instruments available in Puglia Sviluppo. So hopefully, if there are any other companies here, I have seen a couple, or startups, as well as Array itself. If you're interested in the equity fund, you can either contact us or contact directly the asset management companies. And for everything else, obviously, we're just a phone call away. So thank you.
Teresa Malloy, Puglia Sviluppo. We'll also meet you in a few minutes, the third and final session. But now it's time for the final guest of the second session. I imagine you all know about the Grottaglie spaceport project. It represents a milestone in Italy's space ambitions, serving as a critical infrastructure for research, testing, and commercial spaceflight operations. So, I invite on stage Patrizio Summa, who will be speaking about the strategic vision of the spaceport, its capabilities, and its potential to attract international aerospace industry players. The floor is yours.
Si sente? Okay. Good afternoon. Thank you for the invitation. I'm Patrizio Summa. I'm the director of special project in Aeroporti di Puglia. Aeroporti di Puglia is the management company of the airport network of Apulia region. In this way, the Aeroporti di Puglia is a main shareholder, the Regione Puglia, and then is an arm of Apulia region in airport and infrastructural operations for this, in this matter. We manage 4 airports, Bari, Brindisi, Foggia and Grottaglie. Then we have specialized each airport to a specific vocation. Bari and Brindisi for commercial operations, Foggia for logistic and civil protection operation, and Grottaglie for industrial and aerospace operation. In order to make a network, to enforce the capability of Apulia region in order to attract investments in airport sector. In 2014, ENAC, the Civil Aviation Authority in Italy, designed the airport of Grottaglie as test bed for unmanned aircraft operation. This is the beginning of the story of Grottaglie. With the Aerospace Technological District in Puglia, with the University and Politecnico of Bari, all of these stakeholders has created an environment, the ideal environment in order to develop a special infrastructure for industrial and aerospace operations in our field. In 2018, the Italian government makes a selection of all the airport infrastructure in Italy that has the requirements requested by specific rules of the Federal Aviation Administration, that is the American Civil Aviation Authority, in order to develop a spaceport. In this selection, only Grottaglie Airport has passed this proof, this test, because Grottaglie is an infrastructure with a lot of special requirements. The length of the runway, 3,200 meters, the airspace dedicated, a corridor that brings the operation to the sea, lack of traffic, of ordinary commercial traffic. Then the Civil Aviation Authority selected Grottaglie, and Grottaglie in 2018 has been designed by the Italian Ministry of Transportation as the first, the only one spaceport in Italy, but for horizontal operations, this is the spaceport of Europe. Because the spaceport for vertical operation we can find also in other countries, but for horizontal operations, the only one with this characteristic in Europe is Grottaglie. Then we have engaged by Regione Puglia and ENAC, the Civil Aviation Authority, to design the infrastructure. Because the spaceport is a special infrastructure that needs some requirements, distance, characteristic of the apron, of the hangar, of the fuel facilities, all of these services, special services, in order to tackle all the issues for these special operations. Then Aeroporti di Puglia has engaged a team with the coordination of Aeroporti di Roma Engineering, and then we have the design. We have designed the infrastructure. That is an infrastructure flexible. It's a strange link, infrastructure and flexibility. But the infrastructure has been designed for multi-purpose, multi-operator operations. Not only suborbital flights, not only avio launch of satellite, not only return to base of spatial operations, but all kind of aerospatial or aeronautical operations can be developed and in this infrastructure. The design has been sent to the approval of ENAC, that is the Civil Aviation Authority that approved all this design. And the design has also created a development of the area of the airport, of the areas of the airports, because not only the spaceport is host in the airport, in all the facilities, but also industrial facilities like Leonardo. In Grottaglie, Leonardo produced the fuselage of the Boeing 787, the converted plane, and other production. And then the Grottaglie now has been a special industrial area for aerospace and aeronautical operations and productions. The infrastructure now is waiting only the last requirements in order to close the operation and then begin the realization. In this moment, in this hour, at 17, we will begin. We are designing a feasibility study for operational issues with Virgin Galactic, that is the operator selected with ENAC for operate suborbital flights in Grottaglie. ENAC and Virgin Galactic has subscribed an agreement that is in these days will be developed in order to define all the operation in Grottaglie. Then the result of this feasibility study will be acquired by us in order to ultimate the final release of the infrastructure of the spaceport of Grottaglie. Then, for us, it is a great an honor to work for this target, because the spaceport is a special infrastructure that we have the privilege to have in Puglia, because this spaceport is located in Puglia, but this is the spaceport of Italy, of our nation, of our countries, because it's a special infrastructure that will bring us all types of environments, research, collaborations with stakeholders, all kinds of collaboration that will develop our land. And for this, we are very, very pleased to work for this. Thank you.
Thank you. Thank you, Patrizio Summa. See you soon in 20 minutes. Thank you so much. Because before we continue with the concluding roundtable, I think it's time for a break. And we're in Italy. So see you in 20 minutes. In the meantime, enjoy a good coffee. Thank you. Signore e signori, scusatemi, è stato trovato un portafoglio nel bagno delle signore. Basta, quindi chi l'avesse perso l'abbiamo trovato. Chiedo scusa di nuovo, non un portafoglio ma un telefono. Signore e signori, ricominceremmo. Ladies and gentlemen, we'll start in 2 minutes, so please take a seat. For the questions, this, okay? Okay, we go. Take a seat or where you want, where you want. Okay. I would like to thank you another time, our guests, Danny Olivas, Eleonora Zanus, Antonio Mattia Grande, Adele Luta, Teresa Malloy, Patrizio Summa. Yeah, okay, yeah. Here we go? Yeah. So, I have a little but difficult challenge. Only 2 minutes each answer, okay? Good for you? Two round. Let's go, Mr. Olivas. Based on your experience, what were the most challenging aspects of working in EVA suit, and how have these challenges influenced the design of the next generation of suits?
So the two of the greatest challenges that we had in the suit is one with mobility and fit. The suits that were designed for the International Space Station that evolved out of the space shuttle spacesuits. And as modular as they were, they fit a small percent or a smaller fraction of the entire astronaut corps. And even those who did wear those suits, because of the limitations and the joint mobility, it led to often injury of astronauts. I was fortunate that I didn't have that issue. So mobility and fit is one major issue, and that's in the pressure garment system, so that is a challenge for that community. Then it's also the life support system, the thing that keeps you alive. So things such as batteries that are designed for space application are taking advantage of new and innovative ways to manage the things that astronauts care about. Staying cool inside the spacesuit because you build up a very high metabolic rate and heat load as you're working. And then also taking advantage of new technology such as CO2 scrubbing. One of the limiting factors on the spacesuit currently is the metal oxide canister, which is a bed which absorbs CO2. Once that bed becomes saturated, you have to cancel the spacewalk. But technology that's being built today is looking at taking beds which regenerate in the environment. So a vacuum environment, you have 2 beds, it rotates back and forth, and so as you are consuming one bed, you're venting the other one to the vacuum environment. But these are all brand new technologies. They have demonstrated themselves in the relevant test environments, but they have yet to really be fully deployed in a spacesuit. So there is lots of opportunity both on the outside, you know, the pressure garment system, as well as in the primary life support system. Is that 2?
Maybe, perfect. Thank you so much. And Eleonora Zanus, what are the most promising materials currently being tested for EVA suits that will operate in the harsh conditions of Mars?
I got it. Well, we are looking into fabrics, because they have very cool properties. Then one of the major problems is that you want the spacesuit to protect the astronauts, so you need the hard properties of hard materials and composite. So what we are doing right now is to look into those fabrics that provide all the pros of fabrics. So they are light, easy to mold, easy to sew and to seal with others, and combine them with the properties of fabrics that, for example, don't have any elasticity and can provide all the hardness that you actually need.
Yeah.
So the idea is to provide a suit that's it has hard components, but it's lightweight as it were just a soft suit. So we were looking into adding external coating, for example, to fabrics coming from other metal, for example, for radiation protection, these kind of things, but also from other applications, for example, fireworks or fireman jackets, bulletproof jackets, and so on.
Thank you so much. And speaking of materials, Antonio Mattiagrande, how do self-healing materials work, and what is their potential in improving the durability and safety of EVA suits?
So, self-healing material works basically following biomimicry principle.
Yeah.
So, you need a phase that is moving inside the material in order to close potential damage. This flow of material, of moving of material, is the focus of self-healing, because without that you cannot have a close of a crack. Regarding the application of spacesuit, is very challenging because you need several properties be combined in the same material. Yeah. So you need the material have to resist to space environment. So not only capability of self-healing, but also capability to stay in space, especially regarding radiation. So we saw that radiation have an effect on the performance of self-healing material, but probably the trigger for application in spacesuit will be exploit the environment, because the moving of these dynamic bonds of the phase change material inside the self-healing system can be tuned by application of energy. There can be change of temperature, but also, for example, radiation that give mobility to the phase. So this can be an opportunity to be tested.
Yes, of course. And Adel Luta, okay, as scuba diver, I will ask you this question. How has portable life support technology evolved from the shuttle and ISS era to the upcoming Artemis missions? And what about the application here on Earth?
Yeah, that's a great question. I think Danny already mentioned one with the CO2 scrubbing. That's going to be a big game changer for us. I think also the electronics. So the original spacesuits were designed in the 1970s, and there's so much opportunity for electronics and computer processing. We've been able to upgrade the battery over time, but there's still work that can be done there. So just that suit is 40 years old, so there's going to be so many more things coming just because we can't use any of the original parts. But I think the technologies, the CO2 scrubbing is really going to be amazing. Some of the suit will be able to be used on Mars, but some components will have to be discovered new. So NASA's Moon to Mars efforts are already looking to fund things that are unique on Mars, and then if you can show what the changes are, they're willing to give you funding much earlier on. So that is something to look into, because I know Artemis is lunar, but the Mars efforts already have a roadmap that people can research online.
Thank you. And Teresa Malloy, what funding mechanisms are available in Puglia and Europe to support innovation in this field?
For the spacesuits?
Yeah.
Okay. Well, it basically depends on the type of company that's working on it. If it's a startup, as I mentioned, we have the regional government has its own funding mechanism for startups. But also, I think these days, most regions have similar incentive schemes. And also, the Italian government, through its agency called Invitalia, has 2 or 3 different programs. So for initial development of innovative products like this and spacesuits, there are mechanisms, quite a lot of mechanisms out there that companies can rely on. Obviously, once the company starts becoming a bit bigger, then, and maybe requiring more funding, that's when it becomes a bit more difficult to step in with public finance, because obviously there are various regulations on what's called state aid within the European Union in particular. But we do also have various mechanisms that can support even multinational companies developing their business ideas.
Thank you. The next one is for Patrizio Suma. Patrizio, could Grottaglie play a role in testing EVA suits or simulating surface operations for lunar and Mars missions?
I think yes, because the spaceport of Grottaglie will host all types of operation for preparing all types of special operations. The infrastructure of the spaceport will be composed of an apron, an hangar, but also a polyfunctional, a multi-purpose building for training, preparations, and other leisure the operation for preparing and to have a nearest with the visitors, and not only for specialized operators, but also for all kind of people, university students, researchers, but normal people that will have the pleasure to stay in a building that will create a special environment for space.
Thank you. Danny, 2 weeks ago, during the inauguration day, President Donald Trump set a new horizon, Mars. So my question is, how are you or your company prepared to respond to a change in policy, should one occur, obviously?
So one of the areas that I have been involved in recently, and you've heard some discussion about the zero-G plane. I find that very interesting. I actually came across those services when I was doing the spacesuit development, and you saw Adele in there, and if you saw the back of the head, that was me in there as well, the little bald spot. But those kinds of technologies and those kind of services are really what I think are going to be key to sustainability in a space ecosystem. And that is one where there's flexibility in the platform that you're operating in. We know that at least for the time being, we currently have the Artemis program, and that's a lunar destination. The gravitational environment there is different than it is on Mars, and it's also different than it is on ISS. So in my collaboration with the Zero-G Corporation is that, that's a test bed, for example, that you can decide which reduced gravity environment you want to operate in, Zero-G, Lunar G, Martian G. And you can just change the attitude of the plane, and you can then test in that field. So I think those kinds of technologies and services where you're thinking ahead of how things could possibly change. As I said, space is space. The moon is the moon, Mars is Mars. And so those technologies, whether you're talking about a spacesuit or whether you're talking about test facilities or even pieces of equipment, you have to be thinking about how would this operate if tomorrow things change, because often in space, the tomorrow is unknown, right? And you only know about it once you're there. So we don't know, it's a long road between now and the time we go to Mars, so it's possible that things are going to change, but for right now, the focus is in Artemis, but again, it's that design and flexibility gives us, I think, any company or any organization or any agency the ability to be successful regardless of what the future is of space.
How many years before Mars? 2, 4, more?
Well, so here, think of it this. So in order for us to get to Mars, we talked about how when you get to Mars, you want to go out and you want to do a walk because you want to pick up rocks, you want to look for resources, you have to fix your ship. We don't currently have a suit that's designed for Mars. We don't even have one right now that's certified to go back to the moon. So this is all stuff that has to happen. Normally, that development cycle for the spacesuit, the first one took 6 years. This is the one, the Apollo suit, and it was an evolutionary design. Yeah. The current suit that was that's being designed for the lunar missions, they spent many, many years working on improvements, like Adele had mentioned, the CO2 scrubber. That technology was actually baselined in 2008, but it's just been evolved over time. So there's been elements that they've been working on, and even today, we still don't have a suit that's ready to go to the moon. But if you're going to go to Mars, you probably need to have something like that, as well as the transportation to get you there, which we don't have right now either. So everybody's working on their own little areas. SpaceX is working on, the Starliner. They're looking at in situ refueling for basically further destinations. There's lots of technology that has to develop. So I think any organization has to just think, okay, we're going to focus on this, but recognizing that we have to be adaptable in other, depending on how things might change.
Eleonora, speaking of new destinations and new challenges, maybe, how do you envisage testing new materials before they are used in actual space missions?
Well, there are many different approaches to test a material. You can go for analogs. It depends on what you want to test. So if you want to go for mechanical properties, you can simulate the environmental challenges that you want to tackle. If you want to see how they perform through usage, you can go for analog missions in different setups. So you can do, for example, underwater missions, you can do missions in the desert. So there are different options there that are way more viable and more economic. And then you can finally go through smaller sample testing in space itself, for example, before applying the material at a bigger application. So that really depends on the purpose. So of course, like everything, you got to create a roadmap for the development and define the objectives, and based on that, define what's your purpose. So, for example, in terms of fabrics, of course, or the material we are looking to, we can go for in testing in extreme environments, but then also how you apply them to a suit and how the material interacts with each other's, building multi-layered layups.
You think also zero-G flights are a good environment for test new solutions, or?
Yeah, absolutely.
Okay. And Antonio, how can self-healing materials improve safety and reduce the risk of catastrophic damage during extravehicular activities?
Yeah, this is the purpose of the development of self-healing material. We want that small damages does not propagate inside the spacesuit, or also inside maybe a space structure. So this is the role of self-healing material. Avoid that a small damage, increase in dimension, propagate, and give a catastrophic failure. So we want to heal small damages in order to avoid the growing.
Yes.
So yes. This is the way we face the risk of catastrophic failure.
And Adele, could AI-driven diagnostic and real-time monitoring improve the safety and efficiency of astronauts' life support systems?
The whole industry is already looking at incorporating human-machine teaming, so augmenting decision making. So Orion has already brought a whole bunch of systems on board in which the software can do certain things, and then it engages with the human at a certain decision point. So it's more than machine learning. It's already kind of a joint team. I think for AI, we're not quite there yet, but we were talking about designing the spacesuit to do similar things, just because you won't have mission control as close. And so you'll still want to have the human in the loop, but you'll want the suit to be smarter in terms of what capabilities they have today. Yeah.
And Teresa, we have institutions here, private companies. How can regional funding encourage collaboration between research institutions and private companies working on spacesuit technology?
Well, I think I mentioned it before to one of the startups here.
Yeah.
From our point of view, all of the funding available must be channeled towards innovative initiatives. That means for us the emphasis is on research and development, not on building factories, not on investing in buildings or machinery. It's about how you're going to make your products more competitive, how you're going to introduce new business solutions, new services, including in the space sector. So for any, I said before, we have various funding initiatives available for all sizes of companies, from startups all the way up to multinationals. But the first thing we want to know when they come to us with an application is, what is your plan for research and development? What are you going to improve? What are you going to do better than what you've been doing before, or what's already out there on the market? If they come up with a viable research and development plan, then we go forward with the application process. Otherwise, if they're just looking for money, as I said, to build a new factory, to build a new company, we are not really that interested.
Patrizio, last question is for you. Same topic, but from a different point of view. How does the spaceport facilitate collaboration between research institutions and the commercial space sector?
Regione Puglia and Aeroporti di Puglia with ENAC, ENAV, that is the ATM authority, and CIRA, this is the Center of Research of Campania, has created a body named Cryptalie Spaceport, is the ancient name of Grottaglie, that is a scientific body that will encourage this collaboration with all the people, all the stakeholders that in research, in industrial, in commercial, in many sectors will collaborate in order to develop this project.
Thank you so much. Excuse me, Danny, Adele and Teresa, I will switch in Italian for 2 minutes, perché permettetemi di ringraziare i nostri ospiti, perché spesso e volentieri, soprattutto per chi fa il mio mestiere, per chi racconta lo spazio, parlare di futuro sembra parlare di qualcosa di sostanzialmente astratto. Tecnicamente il futuro non esiste, adesso senza scomodare chissà quale filosofia orientale. Ma io credo che eventi come questo e soprattutto ospiti di questo livello dimostrino come in realtà, sebbene non esista, il futuro è esattamente quello che si fa giorno dopo giorno, è quello che si costruisce giorno dopo giorno. Per cui ringrazio tutti i nostri 6 ospiti. Thank you so much for your speeches. I'm very honored to be here. Thank you so much. Grazie, grazie, grazie. Ma prima di concludere, credo che la cosa migliore da fare sia ringraziare una persona che ha reso possibile questo incontro e che adesso chiamo sul palco perché darà una sua panoramica conclusiva, quindi sono onorato di chiamare su questo palco, che non è un palco, il generale Roberto Vittori. Thank you so much.
Grazie Emilio, farò un pochino di pratica di italiano per Danny, vero Danny? Devi dire sì, devi dire sì.
But we want me to do what again?
Say sì, sì, yes.
Say sì.
Bravo, bravo, un applauso per Danny. Stava dormendo, l'ho svegliato. Spanish is very similar to Italian, right?
Sì.
I have my third son that is a double high school diploma in English and in Spanish. So I will have you to talk to him. Grazie Emilio, grazie a tutti per questo importante ragionamento assieme. Qual è l'idea? Rubo 2 minuti soltanto. All'inizio avevamo fatto la Luna come sfondo. Di solito non seguo le mode, no, stavolta ho cambiato, e tra la bozza iniziale e quest'altra è successo quello che è successo negli Stati Uniti. Quindi qual è la cosa più probabile nei prossimi dove andremo? Guardate la fase tra Terra e Marte, perché a occhio sicuramente partirà uno Starship per Marte ogni qualvolta la Terra e Marte saranno in fase. Quindi mi sembra che il primo giro sarà tra 2 anni e il giro successivo 2028. Che significa questo? Significa che lo Starship è gigantesco, quindi ci saranno tante cose che vanno. Qual è la direzione? Dove stiamo andando? Basta che guardate Starlink. Starlink che cos'è? È nato non so quanti anni fa, non mi ricordo, come un'idea. Adesso lanciano su decine, centinaia, migliaia di satelliti. Questa è l'impostazione che ha dato Musk e questo è quello che vedremo nei prossimi anni, quando Musk ci avrà un'influenza importante all'interno del mondo americano, che è quello che dà il là. E lui vuole costruire tante di queste Starship e vuole andare verso Marte. La Luna gli interessa poco, con Marte sì, secondo me sbaglia. La Luna, le scale si fanno gradino alla volta, quindi la prossima frontiera è sicuramente Luna, però lui andrà su Marte e ci avrà tanto spazio per tante idee, esperimenti. Lui non vuole far tutto, vuole semplicemente pensare al trasporto. Da qua era partita l'idea di allineare alcune eccellenze americane e italiane e cercare di cominciare a ragionare se a un certo punto ci troviamo su Marte. L'idea mia è sicuramente non ci mettiamo astronauti, ma almeno un manichino a bordo che possa in qualche modo raccogliere dati, radiazioni su tutto il viaggio, sul momento del rientro, l'atterraggio e quant'altro. Questa è stata l'idea alla base del quale ho chiesto a Danny. I was saying that the idea behind our chat in Los Angeles, and out of which we decide to get here and to get organized, the idea to create a collaboration between Italy and the US, focusing on something that in the US, for one reason or the other, is now in an uncertain future, EVA suit. And we have Rea in Italy. We have energy and enthusiasm. We have infrastructures, the spaceport. We have people that believe in investing in innovation. And we have who can do the job. We have all the ingredients. Let's get it done, right? Yeah. Grazie Emilio e alla prossima puntata.
Thank you so much to you. It's been a great pleasure and a great honor being here. And thank you to Danny Olivas, Eleonora Zanus, Antonio Mattiagrande, Adele Luta, Teresa Malloy e Patrizio Summa. Thank you so much. Grazie davvero. E come dicono gli astronauti, per aspera, ad astra.